What's up, everybody? Welcome to another exciting lecture of Trig. Today is lecture 17. We're going over section 3.3. Before we really get into everything, I need to introduce a new structure to y'all. But to introduce this new structure, I wanted to compare it to something else. So what I've got behind me are examples of these two different structures. In math, we have what's called a scalar. The scalar is just a number, really. It's a magnitude. But what if we wanted to represent something like these? Things with not just a magnitude, but also a direction. So for example, we've got all of these directed line segments, right? And they're representing things with some sort of a direction. Right, so for example, we've got U going from this point up to here, and it's going in this direction. And we've got V going from this point in this direction, right? And it ends here. And we've got R and we've got S, and we could write a bunch of others. Doesn't matter. Bunch of these things. These things are called vectors. Vectors are mathematical objects that have not just a magnitude, like our point A here, which has a magnitude of 5. No, a vector has a magnitude and a direction. And when we represent a vector with a line segment, a directed line segment like these, we represent the magnitude of the vector by the length of the vector. So another way to think about magnitude when talking about vectors is to talk about the length of a vector. Okay, so how are we going to write these mathematically? Like, how are we going to show these in equations? How are we going to talk about them? That's the next obvious question, right? Well, I'm happy you asked, because that's what we're going to talk about in just a second. Now, before we really get into the meat of all of this, before we really start talking about how we show these structures mathematically, how we write them and use them and play with them, before we go there, let's just look at two different vectors. We've got the vector u and we've got the vector v. U is the vector from the point Q to the point P. So we're going from the origin to the point 3, 2. Now vector V is from the point R to the point S. So V goes from the point 1, 2 to the point 4, 4. Now you might be looking at these saying, okay, so what? What do we do with them? Well, one thing we might want to do with them is talk about whether or not these vectors are equivalent. Well, in this case, you might be looking at it being like, these vectors aren't in the same spot, they're not over top of each other, they're not equivalent. Wrong. That would actually not be the case, because they are equivalent. These are equivalent. So you might be now asking, but how? They're not on top of each other. That doesn't seem like a thing. It is. When two vectors are said to be equivalent, they have to have two things in common: their direction and their magnitude. Okay, well, how are we going to talk about that here? How are we going to talk about their directions? One way we can talk about their directions is by looking at the slope of these two vectors. Okay, so let's do that. The slope in quotations, because slope, it's not really the slope, it's not an equation, right? But we can think of this slantedness. The slope of u would be 3, my mistake, would be 2 minus 0 divided by 3 minus 0. So it would be 2/3. And the slope, the slantedness of V would be 4 minus 2 divided by 4 minus 1. Or, again, 2 over 3. Now, how did I do that? What did I just do here? Well, talking about the slope, the slantedness of these two different vectors, what I did is I said, go from your final y position and subtract your initial y position and divide that by your final x position minus your initial x position. That'll give you the slope, the slantedness of these vectors. Okay, so they have the same slant to them, right? So if they're slanted in the same way, they must be pointing in the same direction. That's the idea here. Okay, well, what about the length? What about the length of these things? Because that's the magnitude, right? I said, in order for them to be equivalent, they have to have the same direction and the same magnitude. How are we going to find the length of these? Well, we're just going to apply the Pythagorean theorem. We're going to say, all right, let's imagine a hypothetical vector. This hypothetical vector is going to look like this. And we're going to call it the vector A. Well, A is going to move in the x direction so far and in the y direction so far. So it's going to have a change in the length in one direction and a change in the length in the other direction. So if we want to talk about the length of A, we want to find the length of the change in our x direction squared plus the change in our y direction squared, and we want to take the square root of that. In other words, we just want to take and apply the Pythagorean theorem. We want to look at where it started, where it ended, find the change in the x direction, and find the change in the y direction, apply the Pythagorean theorem. We write that in a special way. We say that the length of A, and we use these double lines on either side of our vector. So the length of A is equal to the square root of the change in our x direction squared plus the change in our y direction squared. Now, before I go any further than this, you might have noticed something. Every time I write one of these vectors as just a symbol, A, U, V, whatever, I put an arrow above it. That's how we denote a vector when we're writing it down on paper, on a board, or whatever. In a textbook, we generally use bolded font. So in homework on an exam, you'd want to write it with an arrow above. So like that, right? In the book, it's going to just be bold. Okay, having that gotten out of the way, let's turn back to this problem. We now want to show that the length or the magnitude, I'm going to use a different color for that. Magnitude, I'm just going to write mag for that, which we now know to be the Pythagorean theorem we want to find the magnitude of these vectors. Okay. Well, the magnitude of u is going to be where we started, where we ended, right? Minus where we started in both the x and in the y component. And then we're going to square those and take the square root of that. Okay? So for u, that'll be 3 minus 0 squared plus 2 minus 0 squared, which is going to be equal to 9 plus 4, or the square root of 13. And in the case of v, it's going to be 4 minus 1, that quantity squared, plus 4 minus 2, that quantity squared, which is going to be 3 squared plus 2 squared, or again 13. So we get the square root of 13. All right, so let's review what we just did. We just said that two vectors are equivalent if and only if the direction and the magnitude or length of the vectors are the same. So we found the directions by calculating the slope or slantedness of our vectors. We said, okay, they have the same slope. And then we said, let's find the magnitude or length, and they were the same. So these two vectors must be the same. Okay, that's weird though, right? Because they don't look like they'd be the same. So what are we saying when we say two vectors are equivalent? Well, what we're really saying, what we're really doing, what we're really showing is that if we were to take both vectors and move them so that the tail, the bottom end of our vector, the end opposite of our arrow, we call that the tail. We call the tip of the arrow the head. So if we were to take the tail of our vector and fix it on the origin for both vectors, then their heads would be in the same spot. Which here, that jives, right? Like, if we were to take this vector out of the board, pick it up, hold it in the same direction, and move it down so that the tail was in the origin, well, its head would also be in the same spot. That's all we're saying here. When we say two vectors are equivalent, we're saying that we can move both of the vectors so that their tail are in the origins, and when we do that, their heads would be in the exact same spots. That is all it means. Okay. Still haven't answered the question though of how we show these things, how we write them mathematically. So let's look at that next. So two other names for the end of vectors is the initial point and the terminal point. And when talking about how to write a vector mathematically, what we say is that a vector, in this case v, is equal to, notice these angled brackets, is equal to the difference in your x component, the terminal end minus the initial end, comma, the difference in the y components, the terminal end minus the initial end. that is equal to the length in one direction and the length in the other direction, so v1, v2. So what I am saying is the vector v, because it's equal to the difference in our components, we can say that the vector v is equal to v1, v2, where v1 is the length in the x direction, v2 is the length in the y direction. Okay, but it's going to have a sign associated with it, right? So if v2 is negative, that means we're pointing down. That means our vector is facing a downwards direction. If v1 is negative, that means our vector is moving to the left. If v2 is positive, we're facing up. And if v1 is positive, we're facing to the right. So let's look at an example. What I've got here is the vector x. And the vector x has an initial point r located at the point 1, negative 2, and a terminal point s located at the point negative 3, 2. Now we want to write x in component form. Okay, well, we just talked about it over here. X in component form is going to be angled bracket 1, my mistake, negative 3 minus 1 comma 2 minus negative 2. Close your angle bracket. So what this means then, after we do the algebra, is that the vector x is going to be equal to negative 4, 4. Now look at what just happened. Our y component is positive, so it's facing up. And our x component is negative, so it's facing to the left. Notice also, I'm calling these the x component, the y component. Why is that? Because that's what it's describing. It's quite literally saying you move so many places in the x direction and you move so many places in the y direction. It's also saying if I could pick up this vector and put that terminal end, that initial end, so r, at the origin, the terminal end would sit at the point negative 4, 4. So this is another way then of determining whether or not two vectors are equivalent. If two vectors have the exact same component form, they must be equivalent. Also, what this means is that we can now easily find the length of x. Now we can say, all right, I don't have to calculate the difference anymore because I already have it. If I want to know the magnitude of x, well, that's just going to be the magnitude of x. It's going to be the square root of negative 4 squared plus 4 squared, which in our case is going to be the square root of 32. So this gives us a lot of information really quickly. It lets us compare multiple vectors, right? It lets us see right away if they're equivalent. It also gives us a quicker way of calculating what the length or magnitude of the vector is. All right, so this is math. We're obviously going to do some math with it. What is that going to look like? And what is that going to mean? Let's find out. So the first thing we need to know about math with vectors is what's called scalar multiplication. That's what happens when you take a vector and multiply it by a scalar. So remember, a scalar only has a magnitude. It's just a value. It does not have direction. So a scalar would be something like 2, or -12, or pi, or some other random number that I just can't think of for some reason. Now, when we multiply a vector by a scalar, we're going to have some scalar times our vector is equal to, and we can break this out in component form now, and we can say it's that scalar times the components of our vector, and we can bring that scalar inside to say, look, a scalar times a vector, well, that's going to give me another vector. And that other vector is equal to the component of our original vector times the scalar. So we take the x component, multiply it by the scalar, and we take the y component and we multiply by the scalar, and that's our new vector. So let's look at this. We've got two different vectors here. We've got the vector u, which in component form is the vector 4, 0. And we have the vector v, which in component form is the vector 2, 2. Okay. Now, if we took these vectors, let's say v, and we were to multiply it by 2, what we would have is 2 times the vector 2, 2, which comes out to be the vector 4, 4. Now let's take a moment to think about this. What we've just done is we've stretched our vector by 2 according to this, right? Like that's logically what it seems like we should be saying, right? So let's see if it's true. We want to take a vector of the length 4, 4. We want to put its tail end at the same spot of our original vector v. Okay, well our original vector, the tail of it was at -5, 0. And the head of it was at -3, 2. Okay. So we want to take another vector, like I said, a vector of 4, 4. We want to put its tail at -5, 0 and put its head wherever its head belongs. Well, its head is going to go up 4 into the right 4. So if it goes to the right 4, that's going to be -1. And if it goes up 4, that's going to be 4. So the coordinates for the terminal end of our new vector is going to be -1, 4. Well, that's going to be right about here. So let's mark that really quick. Right about there. So our new vector is going to look something like this. Well, looking at it geometrically, let's compare lengths. Our original vector, about the size of an eraser. If we took that eraser that took the same length and doubled it, well, I'll be damned. It's the same length. It ends in the same spot. So moving our original vector in the same direction as it's pointing and setting its tail, the tail of the new vector. So what I mean to say is Imagine we take our original vector and we clone it. We're going to take this new vector, keep the direction the same, but sit it so that the tail is on the terminal end. It's the same vector that we would get if we took 2 times v and sat it where the terminal end of v started. I mean, where the initial end of v started. In other words, I know that's confusing. In other words, multiplying a vector by a scalar, it's the same thing as creating a new vector that is just that much longer than it. In the same direction, but that much longer. So we have v, and now we have a new vector, which is equal to 2v. It's in the same direction as v, but it's twice the length. Okay, that's a bold claim. Let's check that really quick. We want to see if 2v is actually the same length, or is actually twice as long as what v is. Well, v is the vector 2, 2. So the magnitude of v is going to be the square root of 2 squared plus 2 squared, which is just going to be the square root of 8. The magnitude of 2v is equal to square root of 4 plus the square root of 4. 4 squared plus 4 squared. So it's a square root of 4 squared plus 4 squared, which is equal to 32. So we have the square root of 4 squared plus 4 squared equal to the square root of 32. But hey, wait a minute. 4 times 8 is 32. So really, this is equal to square root of 4 times 8. Well, we can pull the square root apart, right? We can break it up so that it's a square root of 4 times the square root of 8. The square root of 4 is 2. So this is really equal to 2 times the square root of 8. So I'll be damned, this vector is in the exact same direction. This new vector is in the exact same direction as our original vector, and it is in fact twice as long. So when we multiply a vector by a scalar, what we're doing is really stretching or compressing the vector in the direction that it's pointing. So in the case of u, if we were to say multiply it by 3, well, we would take the vector and stretch it to be 3 times as long in the same direction. But what if we wanted to multiply it by negative? What if I multiplied it by -1, for example? Well then, it would look like we took u and just turn it around 180 degrees. That's it. Just rotated it. Okay. Well, what about adding vectors? Let's look at that next. Let's look at how we add vectors. So I personally think vector addition is a little bit more straightforward. And the reason why is because all you gotta do when you're adding 2 vectors together is add them together component by component. So what do I mean? I mean let's say we've got the vector u and the vector v. Well, we can write out the vector u and we can write out the vector v in terms of their components. u1, u2 inside of those angled brackets, plus v1, v2, again inside the angled brackets. Well, then we just put them inside the same bracket. And we say the new vector formed by u plus v is the vector u1 plus v1, comma, u2 plus v2. We just add it component by component. So what does this mean geometrically then? Well, what it means geometrically is, and I'm going to use this as an example, obviously. Let's say we've got the vectors u, which is equal to the components 1, 2, and the vector v with components 2, 1. Well, u plus v is going to come out to be the vector with components 3, 3. So u plus v is 3, 3. Well, we can write this now as a new vector. Think of it as maybe the vector w. Well, this new vector w is going, if we take the tail end of it and we put it on the origin like these other two, it's going to be the vector that looks something like this. Now notice, because this is key here. Notice, if we were to take the vector v and we were to move it along the vector u, so it would sit up here about like this. The terminal end would be touching the terminal end of w. So if we were to move the vector v up here, its terminal end would be touching the terminal end of w. And if we were to do the same trick, but with u, the same thing would happen. So we can think of vector addition in a way, in a geometric way. We can think of it as taking two vectors, picking up one of them, keeping it exactly the same, and just moving it along until the initial end, the tail end of our vector, touches the tip of the terminal end of our other vector. You think of it as just pulling it up, not changing the slant, it has to stay in the same direction, picking it up, and just moving it up along. That's it. All right, so let's play with some of this now. Since we've talked about scalar multiplication and vector addition, let's look at an example that's a little bit more detailed than these. All right, so what we want to do here is, given the vectors u and v, we want to calculate what u plus v is, what 3u minus v is, and then we want to graph them over here. So let's do that. Well, in the case of u plus v, we're just going to add the components, right? Just add them straight through. So what we're going to have is 1 plus -1, comma, 0 plus 3, which is going to be equal to the vector 0, 3. Then we've got the vector 3u minus v. So the first thing we want to do is multiply u by 3. All right. So multiplying u by 3, it's just going to be 3 times 1. So it's going to be 3, 0. Then we want to subtract v from that. So that's going to be -1, 3. Well, wait a minute. I talked about vector addition, not vector subtraction, right? So how are we going to handle this? Well, this is still vector addition. What we've got is 1 plus -1 times our vector. So now we can rewrite this as the vector 3, 0 plus the vector 1, comma 3. My mistake, 1 comma -3. Adding all of these together, we're going to find that our new vector is 4, -3. Okay, so I'm going to have to redraw this coordinate system really quick. The first thing I want us to do from this point is to graph the vectors u and v. The vector u, when its tail is put on the origin, is going to be the vector from 0, 0 to 1, 0, right? And the vector v, when its tail is put at the origin, well, it's going to be the vector from 0, 0 to -1, 3. So that's going to be something like this. So what that means then is that the vector VU, we've already talked about this, it's just going to be this vector V slid across U until the tail end of V is at the terminal end of U. Well, we already did that calculation too. And we know it's going to come to 0, 3, right? So doing that really quickly, we get that the vector looks about like this. And is going to be this vector here. Mind you, these aren't exactly to scale, so if they look a little off to you, that's why. We just want to get these as close to accurate as we can. Okay. Now the vector 3u minus v. Well, we said that comes to 4, -3. Well, we said that that's the vector with the components 4, with the x component 4 and the y component -3. So that vector is going to be way over here and somewhere down here, right? Yeah, absolutely. just based on everything we've got, both in our graph and up here, we know that with our tail end stationed at the origin, this vector goes over 4 units and down 3 units. So it's going to be somewhere over here. Again, not to scale. So that's the vector 3u minus b. So we've seen a couple different ways of finding these. We can consider vectors in a geometric way, like what we've done with the graphs. And we can consider vectors in an algebraic way, like we've done over here. And in both ways, we can find out what vector addition and scalar multiplication will look like given certain conditions, right? Cool. Having said that, I will let y'all go. If you have any questions, by all means, please shoot me an email and I'll be happy to get back to y'all. Have a good one, everyone.